Alrighty, everything should be fine now, at least it. Okay, so if we look at the kind of the definition, right, is that the transfer function has, oops, a numerator polynomial and a denominator polynomial, right? And when d of s goes to 0, h of s goes to infinity, and that's why we call it a pole, right? So as I said before, a lot of times I start confusing the term roots and poles, but in control theory, it's really these poles that are of concern. And we could say we want the real part of the poles to be less than 0, or poles in left-hand plane, right? Definitely not equal to 0. And what is that we're trying to go? Is that's to say the system is in control. And so we've talked about like a single pole here, and that is really something like s plus a, where a is a positive number, right? That's in control, because if I take the step of that, right, I'm going to get something that looks like this, right? This decays down to 0, right? Even if I have this, which leads to that, the whole function decays down to 0. Right? And so really a system in control will settle at some DC value. That's what it does in the time domain, right? Now sure, we can have two poles, right? Which we could have something like this. And now what I'm going to attempt to draw is that kind of S, like second order curve on minus. Okay, is that eventually this exponential to current term decays to 0, and we're left with the DC. Right? And even if I have complex poles where something like this, where the roots are complex, right? I'll have, it goes up, and once the oscillations are decayed, right, it goes to a value. So we basically have our under, over, and critically damped systems. First order systems really don't get a name except being first order systems. All right. Oops. This, I should have done it like that. All right. And you can have, of course, two poles. So anytime you see a pole, there will be an exponential. And if the exponential is on the left-hand side, it'll decay. If it's on the right-hand side, it will exponentially increase. So just as a review, right, two distinct poles, overdamped, repeated poles, critically damped, complex poles, underdamped. Now, there are certainly higher order things. You can have a third order control function or fourth, fifth, eighth, but only second order get these kind of special names, over, critically, under, right? What in a higher order system, you just kind of say if complex poles existed or not, or you might just say, well, there's two complex poles, one set of repeated poles, and this many separate poles, right? You would just, but there's no official name. Now, when we're looking at things, excuse me, so when you're in control, you can have these, specialized names, but out of control, you really don't have specialized names. It's just out of control. All right. So I can have two poles on the right-hand side, and all that means is I have something proportional to exponential increases. All right, now one might be subtracted than the other, but one of these is going to dominate, and it's just going to increase, right? Either positively or negatively, right? I can have repeated poles, but it's just going to increase exponentially. You can even have complex, but there will be an exponential increase. And if you were to plot it, you might, there's just no way to look at the shit. What I'm saying is when out of control, it goes exponentially high or exponentially to negative infinity, and that's the end of it. You don't try to classify it any further. What we're seeking to do is pushing these this way so that we can bring it back in control. Probably did that one a little bit to death, but There are some things that I just wanted to show you that, right? Let's put one pole at 0. All right, and that's an integrator. All right, so the step, right, it's the Laplace transform inverse 1 over s times 1 over s leads to a ramp of t, which is going up. It's not exponentially going up, but it just will, that will never settle, okay? If I have a pair of poles right on the imaginary axis, that's something like this. All right. Essentially, if there's nothing to stop it from exponentially decreasing or exponentially increasing for that matter, if you look at the inverse Laplace transform of that, you're going to get some kind of sine function. So it's like an oscillator. All right. So if you had a pole at 0, but only 1, and it was at 0, right? You're going to get an integrator. Now, sure, I can have a double integrator, triple integrator. That's just going to make it, the waveforms rise faster, right? But having the complex, right, that's what turns it into a sine or a cosine wave. And so in the homework, you're going to see, here's some waveforms, and then you explain where you think the poles are. All right. So you should be able to do that homework assignment now. All right. Any questions before we move on? Okay. So just to summarize what I just said is that if you are looking at the time domain of a step response, right, and you see like this linear shape, well, chances are it's, and you know that it's the step response, right? Well, you know it's an integrator, right? If you see, and that it's out of control, right? But if you see something like, oops, this, where it stabilizes, well, you know it's in control because it's going to a stabilized value, right? If you had a high pass that was underdamped, you could conceivably see something like this. It's oscillating somewhat, but it's, you know, 0 is a DC value, right? And again, if you see some kind of oscillations, right, the poles are purely complex. But if you see some exponential going up or exponential going down, right, it's out of control and it's caused by some pole, right? Maybe not all, but a pole on the right-hand side. Now, it's good to be able to see that, but, you know, mathematically, it would be easier to design our system. Given HS, can you tell if in All right, can you? I think you can. All right. So, well, in fact, this is easy to tell it's out of control because I've already taken, rather than s cubed plus bs, I have an s right there, and you can tell that there's a root, I mean a pole right at 0. All right. So that's fairly easy to see. So things like 1 over s, right? Other first order things, right? You can tell that to make this 0, a has to be positive. So that's easy to tell, right? If we look at a second order system, right, we can use the quadratic equation to find out where the poles are. And so now, really, we can just look at several cases, but if b was a negative number, or this sign was negative, right, then b would be positive and it would be out of control. I don't have to, well, I would have to look at a, all right, but if a were positive, right? So in general, you assume the constants are positive and then there's a sign out there. But basically, if a is positive and c is positive and b is negative, you're going to get a positive root, right? But then what about if b is 0, right? It's totally missing. Well, that's 0, and you get this plus or minus the square root of minus 4ac. Well, there's two cases there, right? If 4ac is greater than 0, you're going to get plus or minus some j. So you're going to get complex poles, you're going to get oscillation. But also if 4ac is less than 0, right, it's positive. But now, I mean, this number is positive, so it's no longer purely imaginary. You're going to have one positive and one negative pole, and that one's going to have exponential increase. And so it will be out of control, right? And then let's look over here. If c equals 0, right? Well, right, there's nothing here, right? Well, you can pull out the s and then see that there's a 0 there, right, at 0. Now, so that's where it comes from, but that's actually a lot of work. All right. And so the thing is what I've found is that when you're looking at an nth degree polynomial, right? So you have, you know, Sn, and we can do this now. Right? There's something called Descartes' rule, which you can use to determine how many and what the poles and zeros are on each side, right? However, we don't actually have to use the full rule, because we just, if there's one pole on the right-hand side, it's out of control. And then it actually summarizes kind of nicely is that all the signs need to be the same. So in this case, I have positive, 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 everything's positive. That will be in control. And then if everything were negative, right, minus n, minus a1. If all these terms were negative, right, it would still be in control. And that's even done, if I have minus s, oops, right, if I have this transfer function, right, really, that's equal to minus 1 s plus 1. So it's easy to see there. So really, if they're all positive, fine. If they're all negative, fine. There's still one more check. No missing terms. All right. So if I had, s cubed plus a1 s squared plus a2 s plus nothing, right? That term is missing, right? You could pull out one s from all of these and have a root, a pole at 0, right? But if any one of these is missing, all it takes is one, then it won't be in control. Now, what if s cubed is missing? Well, it'll be in control if everything else is there, because it's not a third order system. It's really the second order system. All right, bit of a trick question there. All right, so we're going to use this kind of check to really see what needs to be done to bring a system into control. All right. All right. So let's start with an integrator, all right, which, while very useful, right, just mathematically, it's not a system that's in control. Now, yeah, we use a lot of integrators in our DF2, but those filters are in control because we've used feedback to actually bring them into control, all right? But basically, we have a pole at 0. So in order to, we're going to put it into a control system. Right, coming up with a new system. All right, so we have in, we have a transfer function, now we have a new output, and this is our feedback network that we need to then pick a G of S that will bring that into control. But from the signal flow diagram. We have h of s times our input signal minus g of s, h of s. Not everything is a voltage, so we'll just call it out. When we take the ratio of this new system, we have and when you do these enough, where you just have one feedback system, you almost have this memorized, right? Now, you have been working with this, right? We've just kind of called it something different, right? Right? Where we had A1, A2, and we just took V out wherever we needed it. So that's really very similar to what we've already been doing, all right? So let's multiply this out. So when I multiply the denominator through, right, the denominator will actually appear exactly because of this one, the denominator times the one term, right? But then in the second term, it will completely cancel out, right? So now I have a new thing, which we tend to call, which, you know, looks like people call Q of S, all right? Because it's new. It might get a little hard to follow if everything was called H of S. But really, this is still a transfer function. We're just giving it a different name. Now, we need a pole on left-hand side. That means we need some kind of constant here, and it needs to be positive. All right. Running out of room, so all right. So looking at it, it's a first order system, right? So all I really need to do is turn this into something like this, or where b is greater than 0. So let's try, there's three kind of classic things. There's k, proportional, meaning you scale it up or scale it down. Scale it positive, scale it negative, right? Sk, derivative, because in the Laplace, when you multiply by s, right, and take the inverse Laplace of that, you get a derivative of the function, right? And then we get k divided by s, which is our integral. All right. So I'm just going to work with, oops, this right here, so I don't have to rewrite everything. All right. So S plus G of S A. All right, well, let's try them out. So I have S plus KA. I have S plus SKA. And then I have S plus K divided by SA. Now, this is a constant. That's really what we're looking for. And really, all we have to say is KA is greater than 0. All right. Then that'll make sure that this system is in control. While we're just copying that down, right, I can, put in the numerators. All right, just so we don't get lost. But now here, what we find is, well, I have S plus SKA. Well, that's really S1 plus KA. And so that will always be 0. I can make this negative. I can make it positive. I can even make it 0. But this S will always be there. There will always be a pole at 0. So therefore, you can never make this system in control with derivative feedback. Now here, right, I can multiply through by S over S, and I can get S squared plus the S's will cancel, KA. Well, now there's no linear term, right? There's no S term, right? So no matter what I do, I'm going to either have a pair of complex poles which oscillate, or I'm going to have at least one pole on the right-hand side, and I'm going to get an exponentially increasing value. All right. Now in this example, I'm going to kind of make a generically higher order function. Oh, hey Ed, I see you. What's up?
Hi, Professor. For the last slide, how did you get K over SA for the denominator?
Which one?
You went from S plus SKA to S plus K over SA.
Here?
Yeah.
Okay. So I multiplied through by S. So this became S squared.
Oh, okay.
That canceled. Okay.
Okay.
All right.
Thank you.
Thanks. Thanks for your question. Is that it?
Yeah.
Okay. So in this example, we're actually going to have a function of S in the numerator, right? We then will have S cubed plus A1 S squared minus A2S plus A3. So we can rapidly check, right? Are all the terms here, right? Well, yep. S cubed is here, squared, S, and then S to the 0, right? They're all there. So that passes that check. Positive, positive, negative, positive. Oh, right here. That's going to cause it to be out of control. And I really don't have to almost say anything more about it. I just know that there will be some kind of root on the right, or pole on the right-hand side. So this is the term we've got to fix. Or conversely, right, we could make, if we made all of these negative, right, oh, well, then that would work too. But since there's only, it'll be easier to fix this one thing. All right. So we put it into Q of S, right? So I'm going to get the H of S, I'm going to get S cubed. And remember that original kind of Q of S formula for like one feedback path, right? It's 1 plus G of S, H of S, right? So this denominator will be replicated exactly as it is here because of the 1. Right? But then we're going to have the denominator times its own transfer function, and so it will cancel out, and then we're left with the numerator. All right. Well, this actually isn't an improvement because I have cubed, I still have squared, I still have a minus, I still have s to the 0. I just have another cubed thing. So I actually, if I multiply this by a constant, I'm just going to make this bigger or smaller, or I can make it negative, but then it still won't be in control because only one of them will be negative. All right. So what I need to do, right, and I'm just trying to puzzle this one out as if I haven't done this ahead of time, right? I need minus A2S to be positive, you know, some other constant, right? We need the negative to become positive. So I have to somehow convert S cubed, right, into some kind of positive S, right? So K times S cubed is just KS cubed. No help there. SK times S cubed, right, just gives me K S to the 4th. Well, okay, I could have an S to the 4th over here, but this would still be negative. So this one won't work, and this one won't work. Now I could have K divided by S times S cubed, which would give me S squared K. It's not 4th, it's not 3rd, it's not 2nd. I mean, it is 2nd, sorry. But I've actually started heading in the right direction. So let's try K divided by S squared, which now you figured it out at home. That's how I can convert this to an SK, all right? So that basically my transfer function needs to be a double integrator, and I should be able to get this into control. Let's rewrite that. This is what I would get. All right. So now I have my negative thing, I have my positive thing, and so this really would become plus k minus a2s, right? And this just means k minus a2 has to be greater than 0, and that means k just has to be greater than a2, and then I can make that sign flip to positive. Now, if, well, Descartes' rule, I use it, and that's where I figured out how to do it. It gets really difficult really quick if you don't just kind of have the fact that the signs all have to be the same. Because because we can tell wherever the signs are wrong, that's the term that needs fixing. Because we're doing this in a control system, right? Descartes' rule is generic for any polynomial, all right? And so, yeah, we would have our summer. We would have our original integrator, and then our feedback network would be here, and we subtract it. That's our g of s, and that is our original. All right. Now, these are just mathematical models, which can be done, you know, all in op amps, right? But really, a lot of it's these physical systems that we deal with are in fact out of control. And what I'm not showing you is this might be the transfer function of some physical system. And right here, we have some kind of sensor that's outputting a voltage that then maybe goes into a microcontroller that's doing this integration, right? And then the input is being digitized, right, and putting into a microcontroller and having this kind of control system. You can do it all analog as well, but this is a big thing of microcontrollers, where it depends when you took EE30 or not, but you have the MSP430. You might be using a different version, but you have an A to D where you're taking the inputs, and you have more than one because you're taking it from here, right, to bring it in. This could be in, this could be your feedback, right? And then, yeah, you have your out, which is going here, which, yeah, you might have to, you have an analog, a digital to analog converter, but it could actually then need amplifying as you're controlling a motor or something like that, all right? But this is kind of like the heart of robotics, autonomous vehicles, all control systems are like this, all right? Any questions so far?
Can you go back to that previous slide? You have the Q of S is equal to H of S over 1 plus G of S, H of S.
Yeah.
And it's also equal to this, the Q of S below that. Those don't look that similar. I maybe went over that already. Mostly just because I guess the
I guess what it is I was trying to not write out all these polynomials. I was trying to jump to it. Let me
So is it the h of s, the numerator of h of s?
let me try to break it down just a little bit more. But you understand this equation, right?
I think so.
Right. Because the h of s is the system that is out of control that needs controlling, and g of s is going to be the feedback that gets it to be controlled. All right. But it sounds like you're struggling with, I had this, and then all of a sudden I had GSS cubed. Like,
Yeah.
where did that come from? All right, let me see what I can do here. So I have h of s equals s cubed, and I'm just writing it down here. Oops. All right. G of s, you could say I'm pretty sure this is going to work, or I'm proposing this is going to work. All right. So I have Q of s equals our original 1 plus our feedback transfer function and our original transfer function. All right. So h of s. Now, yeah, I'm gonna show mathematically all right. I might run out of space here. All right. Now, sometimes what people will do is, notice how I took this fraction and just put it in straight out terms multiplied by the rest. Some people will try s cubed, and I'm not going to write it all out, right? They'll do this, and I'm not going to write out all of this as well. And this invariably leads to some kind of mistake. Take this whole fraction and just put it straight there. All right. Well, now look, here's the denominator, and there's 1. So I multiply it straight out. And so the whole denominator, oops. This was a minus sign all along. It's all there. Now then, this is the denominator. That's this denominator right here. When I multiply it through, it's going to cancel, and I'm going to get g of s, s cubed. And now, these are the things that I have to work on, right? Now, yeah, I could have another minus sign here, and then I would have to have g of s modify s. I'd have to have some kind of, before we said this would work, right? That could fix that. But then I need to take an s cubed down to nothing. Right? So I might need more than one term to fix all the issues going on. All right. Did that answer your question?
Yeah, totally. That was
Okay.
it. Thank you.
Yeah, okay. Sorry, what happens is when you do these problems a lot, all of a sudden your hand and mind are, I'm not saying they're either connected so well that you're not thinking, or they're disconnected and you're not thinking. Okay. Gotcha. How did the A3 go negative? Oh, that was me just making an example. Sorry. That's a good question. And what I'm going to do is redraw it. Okay. Oh. So what I'm saying is I have a transfer function, and I have the numerator, and I'm just, now what I'm going to do is I'm just going to have s cubed a1, and let's just say plus minus a squared a2s plus minus a3. Now, how would anything get negative? Well, I'd be sitting there making the exam and just decide to make it negative, right? But if you were doing a real control system, it just could happen, right? So if I had s cubed, I could have a1 negative, or this, I could have that negative, and that negative. Well, then it's probably better to make the s cubed negative. That would probably be the quickest way. If I had, let's say I have 1, 2, 3, 4 terms, right? If I have two negative, let's say these two are negative, well, I can make these two negative, or I can make these two positive. It almost, there's no simpler method, all right? But I'm just saying that that's how it could come out. What I did want to do, I'm just scrolling through my notes here, of how could a system kind of become out of control, all right? And I'm just double checking some notes here. Because I wanted a certain example. So this example is in the book, and it's really well documented, all right? But you can have an inverted pendulum, which is like a Segway, right? But I can have a cart, right, on these two wheels. And I can have a mass. I can have the length, right? and I can be on Earth. All right. And so deriving all of that to get this transfer function, it's in the book, which is, it's a really well done example. So I'm not going to repeat how we got it. Okay. All right. So yeah, here's the length of the rod, and it's negative. And that's kind of, if I push the cart this way, right, it's going to go that way. And in fact, the variable is the angle. All right. So it's not, in this case, it's not position, right? It's just the angle. And if you want it to balance, the angle is 0. All right. So if I push the cart this way, the mass goes backwards. So that's why we have the negative sign, right? But thinking about it is that if I start to fall, right, well, then I'm going to start to fall more and more and more and more until I hit, right? And so that's kind of what you could call positive feedback, even though, yes, there's a negative sign here. Positive feedback means you take the output, add it to the input, and makes it go more in the same direction. Negative feedback means you take the output and subtract it from the input, so you go less in the direction that you're headed in. All right. So I can tell this is out of control, not because of the negative sign here, but because of a few issues. All right. One, the signs aren't all the same. So I'm just going to look at this, right? That's positive, that's negative. And there's a missing S term. All right. So let's put it into our equation, our control equation, our control systems equation. So I'm just going to put minus 1 over L. Now, there's the L. A trick at this one is that you might forget that now it's a minus sign. All right. So let's just come over here. So multiply this through. And I think what I'll do is keep the L, not multiply the L through, but so I have S squared minus GL times 1. So I'm going to have S squared minus G divided by the length right there. Then I'm going to multiply it again. So I'm going to have my minus GS, because the original H of S was negative, right? I'm going to have my S squared. This term and this term are going to cancel. And I'm going to have length. All right. Now, I need right? I need everything to be positive, and I need to add that term. Right? So I have to convert my minus g of s times s squared over L. Well, I need a constant, right? I have my, so I have to convert s squared divided by L into a constant. Well, that really just means I need k divided by s squared, right? And I'm going to have two things. But then I also need to turn it into positive. So I have k1 divided by s squared. Now that should take care of that. Oop, my mistake. I forgot about that. So minus gs times s squared minus this has to be greater than 0. All right. So that just means I have still k1 divided by s squared, because that will cancel that out, right? So that's one term taken care of. But now I'm missing the B term altogether. So I have to convert this into something like that. Or no, sorry, that. Well, that really just means g of s is just going to be like an integrator here, right? So if I multiply I'll get that term. And I forgot to carry over the L. Sorry. Previous example. So I've got to keep I'm sorry. When it's all multiplied through, I have to keep this positive right? And then I just have to keep that positive. And then it should be in control. All right. Now, a lot of the questions are, you know, you get an H of S, right? Will proportional feedback work? And then you just go through it, multiply through by K, use K and see if you can get the poles to be on the left-hand side. Then there's other questions, well, will derivative feedback work? That just means G of S equals SK. Integral, that just means K divided by S. All right. Now then proportional plus integral plus derivative, well then you start adding them. So proportional plus derivative, you would use that. Proportional plus integrate, right? PID, K1 plus K2 plus S, K3. And sometimes you might use, not every term might be causing you difficulty, but a PID controller can give you more finer control of the things you want. So you might use it, even though it's in control, you might want to speed something up or slow something down. All right. But that's the way of, like, here's a transfer function, figure out what works, right, is a lot harder than, here's a transfer function, tell me why it's out of control. Will proportional work? Will derivative work? Will integrative work? Or will any of these work? All right, you can see the homework in that. And I think now you should be able to answer every homework question. All right, and next class, we'll go over how we're going to do the exam online. But in summary, when the exam opens, right, you'll be able to download it. And yeah, you could print it and work it out, or just do it on your iPad, do it on a Surface Pro, or just, write out your answers on a piece of paper and scan it just like homework. All right. I see the chat. I'm just trying to find it. Will there still be a practice? I can make up a practice exam. And what we can try to do is I'll kind of publish it at the beginning of class. And what we can is and you guys start working on it, and if you have a question, you can share the screen with me, and then I can see if you're headed in the right direction. All right. But it's probably not going to work exactly like we did last time. But there'll be a practice exam and, solutions. Okay? Alrighty, so I'm going to try to post this video as soon as I can. I'm sorry that the last time hasn't converted yet, but I think between the old videos and today's, you should be able to get all that information. All right. But it's, we're getting really close to the midterm, which is next Monday. And, we'll deal with that as we go. All right. So anyway, take care. I hope you have a nice day and that everything is going well. If you're having an issue, please, it's just better to email you. Okay. All right. Take care.